So today we have Jimmy He from Ohio State University, who is going to talk about symmetries of periodic and free boundary measures.
Yeah, so I guess thanks to all the organizers for the invitation. It's a pleasure to be here. I've already had a lot of very interesting conversations. So the goal for today is going to be to motivate and maybe provide some context, certain symmetries of a particular model of random partition. So I want to really focus more on giving some context because the results I'm going to present ultimately they're identities of symmetric functions. They really could be stated without talking about integrable systems and whatever. But these identities originated from the study of stochastic integrable systems. And I do think they are related. So I want to sort of explain that. And if I have time at the end, I will say something about the proof. But if I don't have time, that's also fine. So feel free to stop me if there are any questions. So maybe, though, at the beginning, I should go a little bit slowly. I'll just give a few definitions. So just we'll recall lambda is a partition if it's so it's for me a partition is going to be a non-increasing sequence of positive integers. K is the length of the partition. I'll call it L. So it's the number of numbers, and I'll usually refer to these numbers as parts. So this would be the first part of my partition. And often we like to draw them using Young diagrams. So to give an example, so this would be the partition 4, 3, 1. There are 4 boxes in the first row, 3 boxes in the second, and 1 in the third. And the length of this partition is 3. Okay. So now maybe the most important definition, which unfortunately is, I don't know that it's so satisfactory. The key player in this talk is going to be something called Macdonald polynomials. So the Macdonald polynomials, P lambda, are a family of symmetric polynomials. So maybe I should say P lambda of x1 up to xn qt. So they depend on 2 parameters q and t and n variables x1 up to xn. And from now on, I'll just write x, but secretly. Okay, so they're a family of symmetric functions characterized by 2 properties. Okay. So one, they satisfy an orthogonality property. So I'm going to define an inner product. Well, let me say they're orthogonal. With respect to the following inner product, the inner product of 2 symmetric polynomials f and g and n variables, it's going to be, okay, there's a 1 over n factorial, which is not so important. Okay, and there's going to be n contour integrals. F of z, g of z inverse, and then some factor delta of z, I guess qt. Okay. And this factor delta, it's not really going to be so important, but let's just give it once. Let me. I can never remember where the t goes. Okay. Okay. So these are these q Pochhammer symbols. So it's a product over increasing with increasing powers of q. And the second property, which is less relevant for us, is that there's some sort of triangularity. So p lambda is equal to a sum over all mu less than or equal to lambda, u mu lambda m mu. Okay, so what are these m mu? These are kind of the obvious basis. You take a monomial, right? So x1 to some power, x2 to some power, and you symmetrize it. Okay, so this obviously gives you a symmetric polynomial. And the point is that the p lambda, you can think of it as saying that they're obtained from these simpler objects by some sort of Gram-Schmidt process, right? This is what these two properties are saying. Okay, so it's not obvious actually that these two properties characterize a unique family of symmetric functions. This has to be shown, but we're just going to assume that they exist and they're uniquely defined. And to fix the normalization, we'll set u lambda lambda equal to 1. Okay. Okay, so usually I just don't define these things. The reason I decided to define them is because actually this orthogonality, in particular the definition of this inner product, plays a key role in what I'm going to talk about. And so we'll see kind of similar formulas appear later on in the talk. And I'll just make the point that the origin of all the formulas is this inner product. Okay, so that's where all our contour integrals are going to come from. Okay, and so finally, what are the measures on partitions? They're defined in terms of these McDonald polynomials. So, maybe let me not make a formal definition, but so we define a measure on lambda by the probability of lambda is proportional to the product p lambda of x, q lambda of x. What is q? Q is just p with a constant in front. And so if you want, you can just put a p here. But in the theory, there's a p and there's a q, so okay. So I think the natural inclination for many people when they first see this definition is to ask themselves, why on earth would you define this measure on partitions? It seems like a strange thing to do. And so let me try and connect it with some things that have appeared in this program. So there are some special cases of McDonald polynomials. When q is equal to 0, they're called Hall-Littlewood. Polynomials. And these turn out to be related in a way that I'll try to make actually more precise later on in this talk, to things like ASEP and the 6-vertex model, okay, which are things that I think most of us are familiar with. When t is equal to 0, these are called q-Whittaker functions. And these turn out to be related to directed polymers. Sort of special directed polymers. So for example, things like the log gamma polymer, and also more exotic things like q push TSEP, whatever that is. But okay. And finally, when q is equal to t, I guess equal to 0, maybe it doesn't really matter. These are called Schur functions. And these turn out to be related to fermionic models. So things like TSEP and Laplace's percolation. So in particular, these have a determinantal structure, okay? And it comes from the fact that Schur functions have some sort of determinantal formula. Okay, so I realize that these are a lot of definitions. This will hopefully be it. But I kind of wanted to at least define the key object in this talk. So are there any questions about anything so far? Okay, so now I can state maybe the motivation for this project, which are some identities that are originally due to Imamura, Mucciconi, and Sasamoto. So I guess I just erased the title, but there are sort of two types of random partitions that we'll look at, right? Periodic and free boundary random partitions. So let me now begin with the periodic setting. In my opinion, actually, the free boundary ones are more interesting, but the periodic ones are easier to talk about. So actually, I will spend maybe more time on the periodic case, and a little less time in the free boundary case. So this is a theorem due to Imamura, Mucciconi, and Sasamoto from 24. Okay, and it's the following identity of symmetric functions. So they show that the sum over all lambda such that lambda 1 is less than or equal to n okay, so this side of the identity, sorry, there's no t is equal to 0. Hopefully it's clear how it's related to this thing, right? This is some sort of expectation, I guess, over this so-called Macdonald measure. And I'll give a slightly different interpretation as well. But once you think of this as being related to the Macdonald measure at t equals 0, this turns out to be equal to a different sum over lambda and mu, such that lambda 1 is less than or equal to n. Q to the size of mu, and then a product of these Schur functions. Okay, so let me define a few things. So what is the size of a partition? It's the number of boxes or the sum of the parts. Okay, so it's the sort of obvious notion of size for a partition. These S's are the Schur functions. So they're what you get if you plug in Q equals T to P. Okay. So, what is S lambda over mu? These are called skew Schur functions. So let me not try and define them. One should imagine that they're kind of like Schur functions, but they now depend on two partitions rather than one. Maybe the only thing I'll say is that they vanish unless the partition mu is contained in the partition lambda. Okay, and it's not so hard to define them, but okay, let's just accept that they exist. So this identity is nice, but why should you care? So let me explain. The point of this identity, I guess. So it turns out that you can reinterpret both sides in a probabilistic manner. So the left-hand side, well, let me just say that the identity is equivalent to the following reinterpretations. The probability that lambda 1 plus chi is less than or equal to n is equal to the probability that mu 1 is less than or equal to n. So here, lambda 1, this is a random variable which is defined according to this measure with t equals 0, right? So it's distributed according to this q-Whittaker measure. Okay, this chi is an independent q geometric. It's not really so important what it is. The point is that this thing comes from this factor. Okay, so it turns out you can reinterpret the sum as a convolution of this random variable against, or measure, I guess, against a different measure. And convolution of measures corresponds to addition of random variables, right? And the right-hand side turns out to be also a random partition, but a different one. This is called a periodic Schur measure. Okay, so this was first, I guess, studied in a paper of Alexei. And maybe the most important thing is that this right-hand side is fermionic, right? So it's defined in terms of the Schur functions, which are fermionic, and so there are determinantal formulas. And so this identity that relates this q-Whittaker measure, which is not fermionic, to this thing implies that well, the left-hand side, the probability that lambda 1 plus chi less than or equal to n is equal to some Fredholm determinant. Okay. And from this, you can then do some sort of asymptotic analysis or whatever. So it actually turns out that this identity leads to interesting probabilistic consequences, even though the identity itself is just a statement about symmetric functions. Okay. So are there any questions about this result? Okay, so what I want to present is basically a direct generalization of this identity. So let me now state one of our results. Maybe, okay, I can put part of it down here, I guess. So this is, I guess I wrote it down, I probably should have said. So everything I'm talking about is joint work with Michael Wheeler. So this appeared less, I guess, 2 years ago now. So let me define Zn P x, y. It's going to be the following thing. So I'm going to write something that's extremely similar to both the left and the right. Okay. It's going to be a sum over lambda and mu, such that lambda 1 is less than or equal to n. There's going to be a u to the size of mu divided by q n minus lambda 1, and then t lambda of x, q lambda, lambda over mu of y. Okay. So if we look at this definition compared to this thing, the point is that if you set u equal to 0, the mu kind of goes away, and you get the left-hand side.
Left-hand side.
Right. Yeah. So when you set u equal to 0, the bottom, this denominator stays, and the p and the q stays, but the mu goes away. And similarly, if you set q equal to 0, the denominator goes away, and this thing becomes a Schur function, but the u stays. So you get the right-hand side. Okay. So this definition is somehow supposed to be a common generalization of both sides. And what we show is that this thing is, maybe I'll put it over here, is symmetric in the variables or the parameters u and q. Okay, so you can swap them without changing the value of this expression. So of course, this implies this result if you set one of the two parameters equal to 0. Okay. So we actually show a bit more, and I want to actually write down a formula, which is maybe, I hope it's not too scary, but okay. So in fact, what we show is that this expression is equal to something. It's equal, okay, so there's a constant, which let's just forget about. And then you get a contour integral that looks a lot like the one that we saw before. So we integrate again over n variables. So the n here is this n, right? Okay, then and we get the following factor. Okay, so you're integrating something relatively simple against some kernel, and the kernel is a little like the one that we used to define the inner product and for Macdonald polynomials, but it's not quite the same. Okay, so this kernel has the following definition. So it has a similar kind of form, but it's not the same. Oh, so hopefully this is not so bad. Right, what is the key point? The key point is that this formula, okay, let's forget about the constant. That's not too hard to compute. This formula is obviously symmetric in u and q, right? So this expression, you know, there's a u and a q here and a uq. and this thing doesn't depend on U or Q. Okay, so if you can prove this, it immediately implies this symmetry. And once you realize that this is what you want to prove, it turns out that proof is actually not so bad. And again, if I have time, I'll say something about it. But really, I think one of the key observations for us was just the fact that this is what we should be looking for, this formula. Okay. Okay, so let me make a few remarks about this result. Okay, so one, this is what I already said. So if, so setting U equals 0 gives this IMS result. On the other hand, so our proof is new, it's different from their proof. Their proof is bijective, which has other benefits. So the IMS proof is bijective. So what do I mean by that, right? I mean, this is an identity of, I guess, certain, functions. You can expand as power series and everything, and they can match up the terms on both sides, okay? For us, we don't see how to do that. So ours is computational. Right, so we just compute and we get what we want. On the other hand, our proof is much shorter than this bijective approach. So I guess that is a benefit. And finally, and this is maybe one of the things that I've been thinking about. So currently, so for now, there doesn't seem to be any new kind of probabilistic consequences. Right, so one of the key motivations of this identity was to match something that's non-fermionic, so something without a determinantal formula or no obvious determinantal formula, with something that did have a determinantal formula, and therefore get some sort of determinantal formula for something that you want to study. Our result, of course, implies this type of thing, but the generalization, right, adding this extra parameter makes both sides equally hard to understand because both sides are now the same, okay? So of course, one could ask whether this formula is of use for trying to take limits or things like this. But as of now, we have not succeeded in using this to do that, okay? Okay, are there any questions about anything so far? Yeah.
Is it possible to add a parameter t in this formula?
That's a good question. We're not sure. Like, probably there is a way to add a t, but things become a lot messier, and it's unclear whether basically, like, I mean, you probably agree that this factor is relatively simple. This will probably become something very bad if there is a t. And so maybe, I mean, at some point, we should probably try to actually work out the details and see if we can even do it. But even if we could, yeah, it's not going to be very well behaved. And it won't have the symmetry. So I mean, I've checked on the computer that the symmetry seems to be lost quite easily. Yeah, question?
Is there any reason to think that if you looked at the inner product defined by taking your delta tilde p instead of the McDonald delta tilde, looked at the orthogonal family of symmetric functions, that it would be a nice family, have nice properties?
Yeah, that's a great question. It's something that I've asked people about and thought a little bit about myself. I mean, the fundamental problem is basically that you don't know whether it actually defines, like, whether it gives you a well-defined family. Okay, so for that, basically you need to show that Gram-Schmidt, like, you need that sort of upper triangularity property that, like, Gram-Schmidt doesn't really depend on the order you do it in. And yeah, we haven't tried really hard to do it. Certainly, I think it's something that, I mean, I'm hoping to think about it more, but at the moment, I don't have a good answer.
u equals 0, you would just get Hall-Littlewood. Is that?
Yeah, well, yeah, at u equal to 0, you just get the Hall-Littlewood kernel. Yeah. Okay, okay, there's no other questions. The second thing I want to do now is to try and connect this back to some sort of integrable stochastic system. So, one might ask whether this generalization has anything to do with the 6-vertex model or ASEP or, whatever. And I want to try and explain that, yes, it has some connection to things that people here care about. And so let me now discuss this relation to, so I call these quasi-periodic. I don't know if this is maybe like, one could also call them time inhomogeneous or something like that. So let me just quickly recall the 6-vertex model weights. So there are 6 types of vertices. So of course, we saw these last week, but let me just quickly define them. So the weights here are 1 and 1. So these are the stochastic weights here. It's 1 minus z over 1 minus tz, z 1 minus t 1 minus tz, t 1 minus z over 1 minus tz, and 1 minus t over 1 minus tz. Okay, so I'd use t rather than the q. That is maybe more often used, and that's because it turns out to be related to the Macdonald t. Okay, so I've defined these weights, and I think we've seen lots of pictures about how one defines the 6-vertex model using these weights. I'm going to draw a slightly strange picture, and I will try. Well, I'll explain why it's a little strange. So, here I have the parameters x1 up to xn, y1 up to ym. Maybe inverted or something. I guess it doesn't. Something like that. So here z is going to be a ratio of the x's and the y's, right? But here I'm going to do something a bit funny. I'm going to put a u times y1 and a u times ym. And I'm also going to connect these to here. So you really should think of it as a somewhat periodic model. So this orange line gets identified with this orange line. Okay, so when an arrow kind of, when an occupied edge leaves the top here, it sort of enters from the bottom here. Okay, but the parameter associated to the line changes as it crosses the orange line. Okay. And this model goes on forever. So, I mean, you can hopefully imagine how it goes. It just keeps wrapping around and around and around. Okay. So, of course, the first question you might ask is if it's infinitely long, like, what's going on? It turns out that actually, very quickly, this model will freeze. And the reason is that, okay, I guess I didn't say. So u in general will be a number less than 1 if we want to do probability. So u is like 0.5 or something. And if you keep accumulating powers of u, right, then the parameter you plug into the model is going to go to 0 very quickly. And once you do, this goes to 1 and this goes to 0. Okay. And so arrows will sort of enter from infinity and travel straight for infinitely long. And then at some point they start moving and wrapping around and so on. Okay, so these types of models have actually appeared before. So in this work of Imamura, I guess maybe a different work of Imamura, Mucciconi, and Sasamoto, some sort of last passage percolation model with a similar type of geometric weights appeared, and also in the open case, these types of models have appeared before, so it's not kind of completely unexpected or foreign that something like this appears, but it's maybe a little different from the usual 6-vertex model. So I now want to define an observable, which is going to be, so this is sort of an infinitely long line. I'm going to want to count the number of arrows crossing this yellow line. Okay, so I mean, I could define it a little more formally, but hopefully it's clear what I mean. I run my model and I just count how many times arrows cross, okay? And by what I said, it's going to be a finite number, right? Even though the line is infinitely long, there will be no crossings after some point, okay? So this is some random number. And the results we showed with Michael is that this observable plus a random shift has the same distribution as, well, something that looks a lot like, okay, this thing. So, okay, there's some constant which we'll just ignore. Okay, so in fact, I've lost this extra convolution in the bottom, so this really is what we call the, I guess, a periodic measure on partitions. We call this the periodic Hall-Littlewood measure. The key point is that the q is 0 and the t is not 0. Okay, so these are Hall-Littlewood rather than q-Whittaker functions. This is not such a big deal because one of the first things you learn about Macdonald polynomials is that you can swap the q and the t. There's a way, there's a sort of algebraic procedure which turns the q equals 0 to the t equals 0 and vice versa. So even though this is Hall-Littlewood, you can kind of pretend they're q-Whittaker. Okay, and so the claim is that these periodic measures, these periodic q-Whittaker and periodic Hall-Littlewood measures, should be related to probabilistic systems that look like this. Okay, so we have not written this down, but we believe that basically any model that you can do this for in this sort of full space setting, so like the log gamma polymer and whatever, there should be an analysis result over here. So there should be some type of log gamma polymer that looks kind of like this, with, you know, maybe not geometrically, but, you know, additively increasing parameters or whatever. And that should be matched to some sort of expression that looks like this. Okay, so you know, at some point maybe this will be written down, but this is just one example of such a result. And so really, if one can study these random partitions, that's saying something about some sort of probabilistic system. So, okay, I call it quasi-periodic because it's periodic, but the parameters are changing. Another way to think about it is that this is a time inhomogeneous system, right? If you view time as kind of this way, then over time, the randomness is kind of changing in strength. Okay, so that's a different way to think about it. Yeah.
So the configuration of your six-vertex model in the first piece, second piece, third piece, are they the same or are they arbitrary?
No. So they're arbitrary. The only periodicity is that like whatever happens here should end up here as well. So I mean, I'm very bad at drawing pictures, so I didn't try. But you should really view this as being on a cylinder. Like you have some sort of cylinder and a six-vertex model kind of wrapped around. So this line kind of wraps around the back of the cylinder and it comes up here.
So if it was a cylinder, you would have the same.
No, or it's a cylinder, but this is kind of like tilted. So it's a cylinder, but this is not drawn like, yeah. I really think will not be able to draw a good picture of this, so I'm not going to try. But I can try later maybe and explain. But yeah, one should imagine that this is wrapped around on a cylinder, but at like maybe a 45-degree angle or something. Okay.
Wait, Jimmy, what are the boundary conditions at the top? Or does it keep going infinitely far to the right, or do you have
No, it goes infinitely far to the left. Right, it goes infinitely far to the left, and here it's free.
Okay.
So at the very end, right, maybe I should have said this. At the very end, the very last box, the arrows come out where they come out, and that's the randomness, that's part of the randomness of the system.
Okay.
Okay, and we're counting just, so we include the arrows that leave the top and not the right, okay? I should maybe say for the experts that one could define a process here and match it with where the arrows exit, but I don't want to try to write that down. Okay. Good. So think that's all I want to say about the periodic case. You know, it's clearly complicated already and quite rich. I want to now talk about some newer work, which is on what we call the free boundary case. Okay. And the whole point, like in the end, what I will tell you is that basically everything we did in the periodic case also happens in the free boundary case. Okay, so in some sense, once I start defining things, you can sort of guess what the results will be. But they're more complicated to write down and maybe parse. So I think it's good to see the periodic setting first. So let me now talk about free boundary. And you can also think free boundary means open, okay, for reasons that I will try to explain. Okay. So let me just directly state the result, and I will sort of give some context. So this is in progress. I don't want to give a time. Like originally, I was hoping to maybe get a lot of work done while we were both here, but as we know, Michael couldn't make it. But I mean, we have the proof written down. We're just currently writing the paper. So let me define this free boundary. Now only depends on one set of variables and not two. And I will define something slightly less general than what we can prove, just because it's a little bit easier. Okay, so lambda prime and mu prime being even just means that the number of each the number of parts of each size is even. So you cannot have only one row of size k. You need at least two rows of size k. Okay, or 4 or 6 or whatever. Okay, and so it's slightly more complicated. So you still have this n minus lambda 1. You have some additional factor, lambda I minus lambda I plus 1, okay, times, I guess I can put this here, u to the mu over 2, p lambda over mu x q0, okay? So notice this is mu u to the size of mu divided by 2, but this is always an integer power because my partitions are even, right? So the size of mu is always going to be an even number. So so the square root is not so important. And this is, yeah, multiplication. So this is kind of an expression that looks a lot like what we had before, like some type of thing like this, except now instead of a product of two p's, we just have one p. Okay, so this is the only real difference. And you can probably guess exactly what the result is going to be. So we show that this thing is symmetric in U and Q. Okay, so the exact same statement. For the experts, one can drop this restriction and put some weights here, these are like Roger-Szego weights, I call them. But I don't really want to define them. So if you know what they are, then you can put them in. And if you don't, then this, I think, is already non-trivial. So we don't need to make these expressions more complicated. Okay, and in fact, not only can we show that this thing is symmetric in U and Q, but we can also write down some sort of contour integral formula for this expression. And unfortunately, the contour integral expression we get is messier. And so I'm going to write part of it down. Essentially because I want to explain that it looks a lot like what we got before. But because it's more complicated, I think I'm not going to try to write down everything. So what we show is that this thing. Okay, so it's some constant times some contour integral. Well, it's the same type of thing. G1 or 2 pi I Zn over 2 pi I. Okay, so Okay, so it looks almost the same as what we had before. What is this plus minus notation? It just means you have the product with the plus sign and also the product with the minus sign, and you multiply those together. Okay, this is going to save me some writing, and you will see in a moment that it's going to save me a lot of writing. Okay, plus something else. The something else is another contour integral that looks a lot like this one. So I'm not going to write it down, but you can imagine it's the same type of thing with some extra factors and whatever. So other. Okay, but let me define delta FB. So this free boundary kernel has the following form. Okay, yeah, well. So in some sense, it's what you expect. You take what we had before, and you just add plus minus signs everywhere. Okay. Okay, so you take the same type of kernel that we had before, but now instead of having, you know, zi over zj, you just have all possible like combinations of multiplication and division. Okay, so you can see why this notation is nice. This is really like a product of like 2 to the 8 different types of factors. Okay, but times something else, which is also relatively simple, but okay, maybe I'll put it down. Oh, so yeah, this one maybe is not so important. The point is that the contour integrals really have the same structure, the same form as before, but the pieces are kind of replaced with analogous objects, okay? And there are good reasons why you expect the integrand, for example, to have this property that it's symmetric not only under permutation of the zi's, but inversion of the zi's, okay? So this kernel now is symmetric in the zi's. It has the so-called BC symmetry. And in fact, this expression also has some type of symmetry in the x's. But again, maybe the most important thing is that this expression is also symmetric in U and Q. Okay, and so once you have some sort of formula like this, it implies the symmetry immediately. Okay, okay, so I realize that this formula is maybe a bit hard to parse, but I at least want to show that the two kernels we get look very similar. Okay, are there any questions about what this is saying? Okay, so let me maybe, I guess I can erase this. Let me make a few remarks. So this formula did not come from nowhere. It generalizes another identity of Imamura, Mucciconi, and Sasamoto. So I mean, yeah, their names appear a lot, so I'll just abbreviate it. Let me just get the year. So in particular, okay, as written, it doesn't quite generalize their identity. You need to add these extra factors that I alluded to, but okay, that can be done. But essentially what they showed is this identity when u is equal to 0, right? And for similar reasons, that turns out to be useful from a probabilistic point of view because it matches something that does not have an obvious Faffian structure to something that, okay, it's still not obvious, but it turns out that it has a Faffian structure, okay? And again, okay, so basically you could just repeat the same comments I made before. Their proof is bijective, our proof is not. You know, a very natural thing to do, of course, would be to try to get a bijective proof of what we showed, maybe using their approach. but so far that hasn't been done. But I want to sort of stress that, at least in my opinion, the free boundary case is both harder and deeper. In particular, the first identity that they showed in this periodic setting, it turns out that there's a few different ways to prove it. So the identity sort of it wasn't exactly known, but it was equivalent to kind of other known identities or things. Whereas this identity, even in the case that they proved, like there are now only two proofs of that identity: their proof and our proof. Okay, and it's really not so easy to show. And even in our case, the proof is harder in this free boundary case than in the periodic case. But I think I will not try and explain the details of that. And so this is one reason why it took us a while after we got the periodic result to get the free boundary result. You do need some new ideas in the proof of this result. Okay. Any yeah.
So
please.
in terms of this picture, the free boundary, what does it look like?
Yeah, that's a perfect question. So let me draw the picture. So as I sort of already said, this is related to open models, right? So you should have some sort of open or quasi-open model. So okay, I don't know if someone has a good name for this. Maybe I think quasi-open is a bit strange, but anyways, I'll draw the picture and you can decide for yourself. So let me not formally define the weights, but essentially there's going to be some sort of boundary vertices that have four possibilities, and they come with some weights. Okay, so this is the bottom boundary, this is the top boundary. You attach some weights here, which okay, we can just forget about. And right, the key, of course, is what does the picture look like? And it looks like the following. So now, put my drawing skills to the test. Okay, so let's go down a bit. Okay, and you get the idea, so it goes on forever. So you kind of have these triangles kind of flip-flopping back and forth, and so really what you have is a strip. Okay, I sort of added some space here to emphasize the triangles, but you don't need them there, and then you'll just get some sort of like diagonal strip in the 6-vertex model. And so at the corners, right, these things correspond to these pictures basically. And okay, in away from the boundary in the bulk, the weights are exactly the same as before. Okay, and of course we need parameters, so this would be x1 up to xn. At the boundary, the parameter inverts. So along the vertical direction, you get x1 to xn, and then along these horizontal lines, you get x1 inverse up to xn inverse. So if you were at Jan's talk, this is you always do this when you have boundaries. But the thing that's not that's maybe different is that once you hit this corner, you additionally multiply by a power of u, right? So this is maybe not so surprising if you look at the periodic case first. So along this line, you would associate the parameter x1 or maybe root u x1, okay? And this up to root u x n, okay? And then you just continue, this, okay? So it's kind of like before. This picture has the standard weights. This picture you get multiplied by root u. This picture you get multiplied by u, and then u to the 3/2, and so on and so forth. Okay, so again, you have these geometrically increasing parameters in your system. Okay, and for similar reasons, this means that after some time, well, time is going this way, but I guess if you look far enough into the past, the model is deterministic. It doesn't really do anything, right? So I'm going to draw some lines. Okay, so there's going to be this yellow line, which is basically like it's between the triangles in the horizontal direction, and there's going to be some orange lines which are between triangles in the vertical direction. And the result that we show, well, actually, let me first define something. So H is going to be the number of unoccupied horizontal edges that are yellow. Sorry, I used my convention. Okay, so the yellow line is horizontal, but the lines that it indicates are vertical. So basically, you count the number of lines here that are occupied, and W or V is going to be the number of unoccupied horizontal lines, so these lines. And what we show is that this is again in our work in progress. What we show is that the distribution of H plus V plus some other shift. So this is no longer a U geometric. It's something slightly more complicated, but let's just, it's some explicit, okay.
What length is
Psi. Sorry, yeah, I mean, it doesn't really matter. I should maybe actually be even a little more careful. Strictly speaking, this in general is not a random variable. It'll be a signed measure. So this is also something that seems to occur quite often in these boundary models as you pick up some signs. So when I write probability, maybe you should really interpret this as convolution of measure, okay? H and V are, of course, random variables. Okay, so this is equal to some sum, which looks a lot like the ones we had before. Okay, so I guess I decided to put these factors in here. Times okay, so it looks basically the same as before. I guess I put in these two factors. The reason is basically you have these four parameters A, B, C, and D. They will correspond to the boundary parameters. So A and B will correspond to the boundary parameters here, and C and D will correspond to the boundary parameters here. And if you were at Jan's talk, they're the same A, B, and C and D that he had. I guess he only had two. He had A and C maybe, but or alpha and gamma or something. But anyways, these play the role of boundary parameters, okay? And so in particular, what this result is saying is, again, okay, subject to the sign thing, the distribution in kind of this, what I call a quasi-open model, is related to the distribution of lambda in some random permutation model, okay? That in this free boundary random permutation model. Okay, and so in particular, one can ask about asymptotics over here. Again, this is kind of like a time inhomogeneous 6-vertex model on a strip. And I think it's actually quite interesting. And even if our formulas, end up not being so useful for asymptotic analysis, I think at the very least they suggest that maybe this model has, more structure than typical or usual. And there could be some other way to study the asymptotics here. Okay, and so, yeah, I don't think I need to go into the proof, so I'll stop there. Thank you for your time.
Questions?
Please, Mike.
Could you just say again, what is the observable there? The number of occupied?
Yeah, so it's basically you're counting the number of occupied, actually I might have screwed, Probably I actually mean this, now that I'm looking at it. Basically, yeah, you're counting the number of occupied edges going this way between triangles and the number of unoccupied edges going up between triangles.
He was correct before because it needs to freeze with all the parts going.
Yeah, we want occupied horizontal.
But if you count the
Sorry, no, yeah, thank you, yeah, right. So when you set it equal to 0, right, there should be 0 unoccupied edges going horizontally and 0 occupied edges going vertically. Yeah, thank you. There were too many negations for me to. So maybe like an example would be like if this edge is occupied and this edge is occupied and this edge is occupied and this edge is occupied, at least in this part of the picture, you would get a contribution of 2 from here and 4 from here. Does that make sense? Yeah. Sorry, did you have a question?
Right, so
Yeah.
what happens in the limit u going to 1? Is it something?
Yeah, that's a good question. And of course, that's the interesting limit. So these, the unfortunate thing is that these observables blow up, right? They go to infinity, and that is sort of obvious. What's interesting is what happens here, and in the periodic setting, what happens in the very last rectangle. It turns out that what comes out is the stationary measure for the truly open or truly periodic model. And this is not, like the heuristic is just that once you put u equals 1, the model is kind of infinitely long, but looks the same everywhere. So it's kind of the periodic, or I guess open model, right? And of course, if you run that infinitely long, you get the stationary measure. So that actually by itself is quite interesting. But it's not clear that what we do says anything about that. So in particular, there are different formulas available. I guess ours is some sort of formula, like new formula perhaps, but it's not clear that it has any benefits over the other ones. It is maybe worth thinking about, but yeah.
Because when u
Yeah.
goes to 1,
Yeah.
so on one you have this symmetry. One quantity blows up because you are counting always the same node. And the other you have the u in the polynomials.
Right.
And
Well,
where
right.
are you
So
going? What is the limit in the polynomial case?
yeah. So because you're dealing with the q-Whittaker case, right? You need to do fusion. So you can't just look at this picture, right? The point is that the same.
Your form is there. The one you wrote.
No, but this is not symmetric at U and Q. So this is the symmetry is not preserved by this Macdonald evolution, right? Because it depends on but it's a good question. Like there is some probabilistic model that has the symmetry, and where things are blowing up for different reasons as U goes to 1 or Q goes to 1. I don't have a great answer for you at the moment. It's something to think about. It is something I've thought about, but I don't have an answer right now.
So I have another question. So you wrote these integral formulas,
Yeah.
and you wrote this source of new measure delta.
Yeah.
So in the theory of these symmetric polynomials, there are other types, variants. Is
Yeah.
there any obvious way of getting some sort of analog of Z for some other symmetry type and check if they imply?
You mean like starting with let's say BC symmetric functions or something like that? Yeah, that's a good question. So I actually sort of suspect that there might be identities like that out there, because there are identities, in some sense, this is like a very decorated version of some type of branching between BC to A and A to BC or whatever. So yeah, so I agree with you that there might be other identities out there if you start with BC symmetric objects instead of type A symmetric objects. We certainly have not, it's something to think about. We have not yet, but it would certainly be interesting.